So, uh, so my name is Mohamed Kassem. I'm the co-founder and CTO of eFabless. My background is actually a mixed background. Started with working in the EDA industry in mentor graphics in Egypt. I started one of the 4 people that started the seed office in the mentor graphics Egypt, and I stayed with them 5 years, and then later went to change into design, and I joined Texas Instruments for in the wireless group. And I primarily, my background was is analog as I started. So many of the phones that are the world had back in when Nokia was the top of the world, and some of these devices here, actually, and these devices on the screen here, the analog can be blamed on me. So either I did something in it, or I was responsible for it. I also I'd love to. This is actually part of my job and part of the curiosity. I did that a lot when I was younger, and then my father did not like these things to happen like this. So I do a lot of tear downs. Unfortunately, not as documented, but actually I have a lot of products that are I buy just to open them up and then close them down, and sometimes stress test them. So this actually is a watch that is powered by the thermal difference, temperature difference between your hand and the watch. And so it's actually, I'll be able to share more maybe later. So what do I mean by making open source chips work? Because it's a high level. So in order for things to work, there are things that need to happen in general as work as the entire initiative of open source chips to actually be successful and continue to progress. As Tim Ansel mentioned yesterday, there is a roadmap, and we need to that roadmap to be energized by the community collaboration and creating something and learning from our failures. And most importantly, we need to keep the ecosystem going. So this is going to be my call to action here, is that we need to go and continue to use what we have to show progress, and then capitalize on that. The more we do it, the more the world is going to do more of open source. A second part, which is actually critical as well, is knowing the process, knowing the technology. So the first thing I say to myself is that if I have a technology, a process technology like Sky 130, for example, we would like, as a designer, I'd like to know what's possible, what's not possible, what are the limits, what you can do and you can't do. And in order to do that, there's no real actual, you're not going to go dig it except through models. And the models, if these models represent the behavior of the technology, so you can use it. So it's a simple, just reason, everybody knows this. However, so it is actually important to know what you care about, and know what your system or design, digital or analog, and what are the dependencies in the process. So this is just a barrage of things, but I'm showing here some of the, like if I talk on analog, there are specific parameters like one over F and GM, GDS, and mismatch, VT mismatch. These numbers actually are essential for to be able to design an amplifier or above, any data converter or so. So the way I look at it, I say, okay, I want to care about these parameters. I want to know that they're actually representative of the real process. Well, that's difficult, because how do I do this? Well, 2 ways. It's either we're verified against documentation that's already available to us and that's available to SkyWater, or actually through the open source community, we actually put structures and measure them and compare and get our own basically correlation data. By doing that, you start gaining confidence in the models. Once you have the models, the fundamental device models are robust, then you can characterize the libraries. You can go far on that. one of the things that I, in my experience, that I had to work with, especially in the device, in a CMOS process. Back in the day, I worked in the year 2000 with TI, and I was working on 180 nanometer. That was the first time we put analog on a CMOS. Well, the process technology, when it was actually targeted to digital design, and it was on-off type of switching. We were required to use these transistors without additional components or masks, rather. So one of the things that they were not happening is that, for example, if you look at the W&L space for a transistor, so that it was focused on the digital. Now we started getting data and saying and defining what would represent clusters of analog needs, and from the size wise, and also we need to actually get into the bias characteristics, not just the on and off. We need to get into points that actually represent an analog behavior. That's just an analog focus, but it's the reason I'm saying that because everything in the library, everything in the PDK that is used for design is built bottoms up on these types of information, whether it's, for example, leakage, drive current, capacitance density, of course, the temperature dependence, and there's an important parameter or important aspect is the reliability, which would, in this case, and for all these shuttles or for all these projects that we're working on right now, we did not dig into it, but this should come, and we'll be able to talk about it later. And actually, I'd like to help get the community to contribute into sharing the knowledge for other people. Of course, the parasitics, and knowing the parasitics, knowing what the metal resistance are, is it sheet resistances or the capacitances, etc. So I'm gonna stop here and know your process. Okay, so by knowing your process, you actually get to a point to either predictable design, or you add margin and you regard for the errors. So I wanted to address the MPW1. What happened? We communicated to the community in different ways about what's happening. So I'm gonna try to actually play what happened here. So we got the wafers, and in the back end here we had as you can see, these are boards. This is the Caravelle boards, and these boards are actually done with the QFN package, just because we want to get it faster, so we can get a head start on identifying and booting up the chip. Now we put it on the system. I actually have a video here, but I don't know if it's going to play because it's a PDF. So it's a video that shows basically the LED light right here, which the cursor is too small to see, but it's on the left here, is flashing. And that was as far as we could get. Okay, after 3 different people testing in 3 different places, and so using just I'm sharing here the Poor Man's Lab. We had myself and Jeff DeCorpo and Tim Edwards, different stations, and we were basically reading the data off on the coming in and out the flash controller, and we're trying to simulate and find out what happened. Well, in this, without reading this data too much, but the important thing here is that it stops at some point, and at some point, basically, that's it. So you can get it to blink, you can get it to fast or slow. We changed the clock frequency. We did several things. But all the time the processor would just stop at some point, and we wanted to explain that. Now we found a lot of sensitivity to the voltage. So some of these things were actually, like this example here, we couldn't get it on the standard voltage for the chip. We got it instead of 1.8. So depending on the chip, we actually had a diversity. So some chips worked on 1.6 volts. So when I say worked on 1.6 volts, meaning you see this pattern at 1.6 volts. Otherwise, if you don't have it on 1.6 volts, it wouldn't actually see it. The second chip was working fine at 1.4. We also characterized it, or without like just putting a heat gun on it, just raising the temperature and lowering it. So we can see that the blinking experiment stops or changes, very sensitive to temperature and voltage. Well, this is a signal for big time hold time violations. We actually did a bunch of simulations, and the difference then is these simulations were actually using parasitic extraction and delay information, SPIF information to create the delay information so we can simulate with it. We were able to see similar behavior. Now, by saying that, we find it in MPW1 jumping, okay, so we have MPW2 and we have MPW3. So basically, what do? I mean, we need to actually act fast and do the right things for the community and for the designs. So when we woke up, we found that, okay, this is MPW2, the masks are not created. MPW3, it's still coming. That was a few weeks ago, by the way. And then we have a chip ignite shuttle. The masks are created. All the masks are created. So we have options here. So if we MPW2, we can actually intersect and be able to correct if we have any hold time violation or so. And MPW3 as it comes later. Now I'm going to take the chip ignite case because it's an interesting case and shows to dig deeper into it and show what we did at high level. So we started, where do we look? So knowing a big part of that was basically the team that is actually designed the Caravelle. They're familiar with the design, and with the simulation experiments, we were able to identify that it's a hold issue to the level where Tim Edwards ran the management SOC part of Caravelle with parasitic extracted data with IRSIM, and was able to see correlated skews for MPW2. So MPW1 is already manufactured. We have a problem. We learned from it, but the priority right away was to actually get to MPW2/3 and the chip ignite version. Well, what we found basically, so this is the timing report on the right-hand side of one of the paths. So the whole time violation was gross. So we get, if you're looking at it, you need to be able to get the clock on two different flip-flops with the combinational data in the middle in a way that meets hold and setup and hold the requirements. So by looking at that report, if you look at the data delay, if you from here you read it, it is 600 picoseconds. It means that the data would actually from the time it's released, it would arrive in 600 picoseconds. However, if you look at the clock, it starts here at 10:26 to 11:77. That's a 1.5 nanoseconds. Well, that means it's actually looks kind of like this. So the data arrives too early, and it's going to flip, and it changes before. It's going to change the other round. It's going to change the previous data. So and you're not going to be able to capture it, right? And then that is actually how it looks like as a whole day. It was 790 picosecond skew. Now, so in order to address this, so what you need is that we need to try to get the clock in the window of the hold of the data. So that means you just take the data and remove. This is the 670, and remove the hold window, and you have like if everything is accurate, and this we have to add margin. You need no more than 600 picoseconds, roughly 600. So how do we do this? How do now we need to go from 1500 1.5 nanoseconds to 600, almost 600. So these are different pictures of on the bottom and on the top right of the management SoC. The one on the bottom left is actually an extracted clock tree of the management SoC alone, and it would be obvious why we extracted it that way. But Tim Edwards basically scavenged into this tree, and through different probing and getting the netlist done, he decided basically that the solution could be addressed with a mesh clock tree. And if you on the top left here, so the kind of difference, there is a clock tree, a standard clock tree, and a clock mesh. The general premise for that is that you get them to closer to the leaves of the tree. You basically have a balanced short-circuited basically mesh of the clock, which is useful in many ways. It's very useful in large chips where the chip on-chip variation is significant or noticeable. So it has the effect of almost like resetting the clock if it's skewed. So the picture on the left is not actually representative with the exact tree of the management SoC, but it is actually representative of the type of the system. So we had 6 buffers here, and then the flip-flops. So Tim applied the change, and then we were restricted because, as I mentioned, in that specific case, the masks were cut. So we're trying to find the cheapest or the least invasive way to repeat or the smallest number of masks, basically, to recut and fix that. So on the top right, these are different connections that Tim did, and then after you do it, you're able to extract it and see it. This is basically the mesh. The difference between this mesh and a standard mesh is that this is after the fact. It was not designed initially to be a mesh. So there's a lot of doubt about how it works and how it's going to solve the problem. Technically, it should reduce that skew significantly. Well, we can't run an STA on the mesh, because what happens in the mesh here is that I get to in the green buffers here, I'm actually short-circuiting, like basically putting all the drivers in one place. And at least as far as I'm concerned, the tools with the current tools that we have do not support that or interpret that. So our savior, basically, we had to go do a SPICE simulation. However, if you go to again back to this picture, this is not a small thing to extract in SPICE. This is a huge circuit, and it is just to get you the size of that tree extracted, including the RC, is you're talking about text files beyond 200 megabytes of size. So it's actually not practical either. So how are we going to do this? We tried Zeiss, So we started simplifying, getting to the point where we say, okay, we see how the tree works, and then looking at the gate level netlist, we take a lot of information from how the buffers are structured, and we know the mesh construction itself. The And then we had to basically create different simplified models for different parts. So we, for example, here, the metal 5, the resistance, this is the power. So we have the power grid that's going different ways. So we created a power grid, and I'll say why we did that. We had to add the decoupling caps, and then we had to add the models for the interconnect, like here in the middle here. And then we had to repeat that because from the gate level netlist, guided by the gate level netlist, we did basically our colleague Karim Farid wrote a Python generator basically to generate for the gate level netlist. So one of the things we did also is we the flip-flops, just got them out of the way as well. So we looked at the Liberty files, came up with with the numbers for the input capacitances of the clock, and then we created that SPICE model. So,
Mohamed, just we're running a bit over time. How much longer have you got left to go on these?
It's actually just a couple more. So.
Okay, cool.
Okay. So. This just shows you the different types of simulations, but in order to gauge what we did, the correction we did. So in the middle top here, this is the kind of a representation of a uniform distribution of the 0 to 1 of the 1 nanosecond skew, and on the left here, how the mesh corrects it. It's not exactly all the points in the mesh are not dead on each other, but it goes down below the 500 per second that I'm talking about. One of the things we worried about here was we need to make sure that there's no power glitches that go down enough that will reset any elliptical. So in order to take all this and fold it into consistent knowledge, we folded into openly, and we provided, as you all know, documentation on how to do it, and then we'll continue to answer questions and address anything that's needed on moving forward. Thank you.